Greetings. In this one, let's look at line graph, which is at line graphs and an example of them. They are graphs which are created when we look at graph G and we monitor which edges have a common vertex. And then we make a line graph, which is another graph derived from it, where its vertices are representing the edges of that original graph, and whose edges represent those pairs of vertices which have which represent edges in the original graph that had a common vertex. So let's look at an example. So if we have G, that is a cycle graph like this. It has three vertices, 1, 2, 3. Well, if we look at its edges and label them ABC, then a line graph of it will actually be quite similar. We will now take the three edges, ABC, ABC, and we connect those that have a common vertex. So AB has a common vertex, BC, and C has a common vertex with B and A. So that's taken care of. So now we basically made an isomorphic relabeled graph as a line graph. But let's look at an example that actually shows a little bit more complicated of the situation. So we can take more vertex, a graph of more vertices, which will be a more complicated example. So let's look at, for example, a graph of 4 vertices, where we have 1, 2, 3, 4, 5, 6 edges, or better yet, let's take one of them. Let's take we can take this actually. We can take this. It's less. It's gonna be faster to draw the line graph derived from it. So again, I will label the edges. So this will be A, this will be B, this will be C. So we have 3 edges, but we will have different connections between them because not all are adjacent. It's not a complete graph. And so I create a new graph, and now, of course, for drawing purposes, we might be more careful about how we draw the vertices, but however we draw them, we can draw a connection. And so let's just draw it arbitrarily. So A, B, C are our 3 vertices that represent the 3 edges in the original graph. And now let's look at each vertex. And in the original graph, we're going to look at the edge with that name and see which edges it has a common vertex with. And those will be, then in L of G we'll have an edge to those representing letters. So the edge C in G has a common vertex with B and A. So we should connect it to B and A. And then let's look at the other one. So edge B only has a common edge with C. So that's taken care of, and edge A only with C. That's taken care of. So we have a similar graph, but because it's not complete, we, for example, don't have the connection AB. There's no common vertex between A and B, and so there's no edge in the line graph. And we can take more complicated examples. This was examples to show how line graphs are derived and what they mean. And also there's one other thing that's very related, called the root graph, which is basically going in the other direction. So if we look at the line graph, we want to see what was the original graph. And also we took into account here simple graphs. So that's good to mention. We had no loops, no directed edges, and no multiple edges between the same vertices or such. Yeah. So all right. So here we looked at so-called line graphs. In other words, we actually line graphs are derived graphs from the original graph G, and what they represent is where we take the edges and draw them as vertices, and then we draw edges between these new vertices the way that we look at the original graph and see there's going to be an edge representing when in the original graph the two edges had a common vertex. So it's a sort of changing the idea. For example, for coloring, for edge coloring, we can change that problem to a vertex coloring problem when we're talking about graph coloring.